3D gaze point localization and visualization using LiDAR-based 3D reconstructions. A solution for accurate 3D points of regard using high-quality 3D reconstructions. Full 3D spatial gaze statistics are retrieved. This data is invaluable for furthering of eye tracking research, specifically free-roaming participants of indoor static scenes. Inputs include a faro laser scanner and a combination of a head-mounted eye tracker with a depth sensor. Our proof of concept capture rig shows the depth camera rigidly placed and in close proximity to the eye tracker. This will increase the accuracy of localizing the head and will also add scene geometry where needed. First step is local alignment using dense slam techniques. Note, we are only interested in locating the roaming depth sensor. The eye tracker itself will be found as an offset at the end of our pipeline. We use frame-to-frame SIFT-based matching on the RGB feed of the depth sensor. We are able to solve for each frame's reconstructed camera parameters from the relative transformation of the matching depth coordinates. However, due to rapid head movements, local alignments may produce disparate camera trajectories with no correlation. Our solution utilizes a global LiDAR map. LiDAR alignments resolve these local trajectories into a globally accurate coordinate system. Global alignment proceeds by first decomposing a LiDAR scan into the format of our previous algorithms. Spherical LiDAR data is decomposed by projecting into a number of planar RGB and depth frames, ensuring proper coverage. Our previous frames are now realigned with the decomposed LiDAR frames to find their best global match. The video on the right is from the depth sensor feed, whereas the present frame on the left is the LiDAR frame chosen in global alignment. Any frames that do not globally align are adjusted relative to their nearest globally aligned neighbor. Here we see a subset of the roaming depth points after local alignment. Global alignment resolves the disparate chunks. ROI annotations using the LiDAR panorama are used to supply region of interest based gaze statistics. They are also used for final verification of the camera trajectory and refinements, as shown in this GUI tool. Lastly, eye tracker offset is computed using a perspective endpoint algorithm and producing the finalized camera odometry. The following shows alignment and simulation results from 4 datasets. The central frame is from the SMI eye tracker video. Our application is built on top of the Unity 3D framework and allows for a number of interactive options. LiDAR models allow for high-resolution UV texturing. Please refer to our paper for more details.